Hello everybody. So in this lecture we are going to look at some illustrative examples where we solve the heat equation using the method of separation of variables, but there are some tricks which come out in a nice way. Okay, so consider a rod which is of length L, length 1 in appropriate units. It's placed along the x-axis. The left end is attached to the origin and the right end is of course at point 1. And let's say that it has this temperature profile sine of pi x at time t equal to 0. Now if the two ends are maintained at 0 temperature and we allow the temperature to evolve as a function of time. So initially it has this profile, but what happens to its profile as a function of time, right? So that's the question. So let's say that the thermal diffusivity is just unity and we obtain the solution by solving the heat equation, right? So we have the heat equation dou capital T by dou T is equal to dou squared capital T by dou x squared. Now subject to these initial and boundary conditions. So the initial condition is that T of x comma 0 is just sine of pi x, and the boundary conditions are at x equal to 0 for all times it must be 0, and at x equal to 1 for all times it must be 0. So this is a Dirichlet problem, right? And we proceed to solve it by the method of separation variables. You write of x of x times theta of t, then you have plug it into the PDE. We have this differential equation, divide throughout by capital T, so you get 1 by theta times d theta by dt is equal to 1 over x d squared x by dx squared, and both sides must necessarily be a constant, which is convenient to put it to be minus mu squared, right? So in these kinds of problems typically it's the temperature is going to decay as a function of time, so it is appropriate to choose minus mu squared, and so the time part is immediately solved and you get theta of t is equal to c times e to the minus mu squared. All of these are standard steps we have seen. Now the spatial part can have a cosine solution or a sine solution, an arbitrarily linear combination is possible in general, and to fit the boundary conditions here you must have x of 0 equal to 0. So if x of 0 equal to 0, then a must be 0, right? So cos will not work here, so we have to work with sine, and also we have when x equal to 1 this must go to 0, so b times sine of mu must be equal to 0, so mu must be some integral multiple of pi. So that's it. So we have got the initial conditions, we have got the boundary conditions. Now we have to plug in this and put in the initial condition. So the full solution in general is going to be given by a Fourier series of this kind. T of x comma t is a summation over e to the minus n squared pi squared t sine of n pi x. But in this very special case we have an initial condition which is particularly convenient. So the initial condition is T of x comma 0 is equal to sine of pi x. So in fact we are not going to get an infinite series, but we will get only one term in this series. So we immediately see that in fact all we need to do is put C1 equal to 1 and all other Cn's are 0, right? So you can look at this a little more closely and convince yourself that indeed for this particular problem it's very simple, and the solution is simply T of x comma t is equal to e to the minus pi squared t sine of pi x. So it's useful to plot this and trace the time evolution of this. So initially the profile is like this, so it has a peak, and then as a function of time it keeps on going down and eventually it goes to 0, right? So one reason I included this solution is because if you remember from our first discussion of a heuristic discussion of the heat equation, we said that initially suppose there is some kind of curvature, we want to model, come up with a PDE which is going to keep on killing this curvature and eventually take it down to a steady state solution, which will be a solution of the Laplace equation, and that's exactly what is going on, right? We use this intuition to develop the PDE, and now we are solving this PDE and we are seeing that indeed that's exactly what it's doing, right? So we'll look at one more example where a subtlety shows up, which is a very close closely related problem to the current problem, but there is an additional subtlety which we will discuss in the next example. So it's the same kind of a rod of length 1 which is along the x-axis. Now the temperature profile is just 0. It's initially at 0 degrees Celsius everywhere, and now suppose you leave the left end at 0, but suddenly you heat up the right end and keep it at 20 degrees Celsius. So now the question is, what will happen to this, the temperature of this rod as a function of time and as a function of space, right? Once again, set thermal diffusivity to be unity. Now, I mean, it's clear that we must solve the heat equation. We are interested in the dynamics, and now the initial condition is a bit different, and the boundary condition is also different, right? So it's just 0 throughout, and so the initial condition here was sine of pi x. So here it is 0, right? So there is no spatial variation at time t equal to 0, but then you crank up this right end to 20 degrees Celsius, and so it's this boundary condition is going to make a difference, as we will see. So the solution itself is a little more complicated, but really it's the same method, right? So everything proceeds as before, except that we must account for this final steady state profile, right? So let's think about it physically. As t goes to infinity, the temperature would settle down to a profile which will be a solution of the Laplace equation, really, right? So in steady state, this part is going to be 0, so no change happens as a function of time. That's what is meant by steady state. So when t becomes very large, dou t by dou t will be 0, so it's going to be just dou squared t by dou x squared, and that is equal to 0, which is nothing but the Laplace equation, right? So at when t is infinity, if the right end is at 20 degrees Celsius and left end is at 0 degrees Celsius, and if the temperature profile must be a solution of the Laplace equation, the way that can happen is if it's a linear growth from 0 to 20 degrees Celsius at x equal to 1. In other words, the steady state solution must be TSS of x equal to 20x. So now, given that, so we know what the temperature profile is at t equal to 0, we know what the temperature profile is at t equal to infinity. So in fact, the Fourier series must be worked out in this manner. So you take this t of x comma t and then subtract out the steady state solution, and all the dynamics is really contained after you have subtracted out the steady state solution. So it is this quantity which is going to be this Fourier series, and in fact to put in, so we'll plug in the initial condition into this form. Now when you do this, you're going to get, so I mean at t equal to 0 is just 0 everywhere, so 0 minus 20x. So the steady state solution we have worked out using our physical intuition, and so you have minus 20x is equal to this Fourier series. Now n goes from 1 to infinity, and now it's not going to be just one term, because in fact all terms will live. You can work out the coefficients. The straightforward exercise in computing coefficients of a Fourier series is just minus 20x. So multiply by an appropriate sine function, integrate out between the limits 0 and 1. There will be this factor of 2 which comes out, when you do this integral, you should check this, and the answer is just 40 divided by n pi with signs alternating, so minus, plus, and so on, minus 1 to the power n. You can write conveniently like this. So the solution is this infinite series. So t of x comma t will be just 20x plus 40 by pi summation over n minus 1 to the so it's going to be minus 1 to the n, e to the minus n squared pi squared t divided by, there is this one, this n, and also sine of n pi x, right? So there is this is the final answer, right, which we can check by plotting it. I mean, I have truncated this series to 100, right? So n goes from 1 to 100. I have made a table, I have taken the sum, and then let me just plot it for you, right? We don't have to go into the syntax of this. So you see that at time t equal to 0, temperature is 20 only here, because I have truncated it at after 100 terms. You see all these fluctuations, but actually it's, all of this is exactly 0. This point alone is at 20, and then as time progresses, you see a smooth variation Okay, so there is some difficulty with this with this plotting. Okay, so we see that, I mean, so the problem is that we are using these exponentials of very tiny, I mean, n big and n going to 100 is going to make this a very tiny number, and that's running into difficulties with the precision. But the key point is that even with just 10, if I keep only 10 terms in this series expansion, I already see that this is pretty good. Only problem is that the representation at time t equal to 0 is not so great, but it's not really a problem, we understand this. And so if you evolve this, the key point to observe here is this tendency to keep on destroying curvature, right? And at some point it's going to become a solution of the Laplace equation. Okay. All right. Thank you. That's all for this lecture.